Alrighty. So thank you all for coming tonight to Applied Track. I know it's a very important day for everyone, that being Ash Wednesday. No. Thank you for being here on Valentine's Day and reminding me that I'm not the only one who's alone. With that being said, who wants candy to start it off? Oh yeah. Woo! Oh, okay. I'm kind of missing. Okay. Yeah. I don't think I saved this. Okay, there's not, these are really light. I can't chuck it all the way to the back. If you want candy, come forward. Any other candy takers? Oh yeah. Okay. You guys don't have to laugh every time I throw one of these. Like, you could say like nice job. No, you got to move close. I cannot, it's not gonna make it all the way back there. If you want candy, come closer. Like, all right. Whoo! Bucket Brigade. Bucket Brigade. All right. Any other takers? No? All right. Well, if you do, I have a bunch. Ryan, you want some? Yeah. Ryan wants. You don't have to laugh at me every time, Eric. All right. So amazing. For today's workshop, we're going to be talking a little bit about recurrent neural networks. Now that, most of you guys have, finished MNIST by now. If not, that's okay. And you've worked most of your way through the Sci-Far 10 notebook. And again, if not, that's totally okay. We're going to be focusing on recurrent neural networks. The attendance code, here we go again. You guys know the deal, the asset cluster, stuff like that. Before we start getting into the actual presentation, a couple of announcements for y'all. So first of all, a little reminder. We have our Is it? Okay, good. It's minimized over there. We have our asset cluster update. We now include the slides and recordings as well. Last week's theory track, was on embeddings, LSTMs, transformers, and large language models. Again, you might not know what those mean. That's totally okay. Really good and very useful if you want to do NLP. Especially, we're going to be doing recurrent neural networks. You may want to, check it out. It'll be pretty interesting. You want Andy? Valentine's Day? Oh yeah. That's my bad. I've been missing. Asset cluster has become so very wide. Also, no theory track next week. I don't know if you guys know, next Monday, President's Day. We love our presidents. Yeah, but because of that, we're not gonna have theory track. Very sorry to disappoint you all. 2 weeks from now, what's on tap for theory track is ensembles and epsilon DP privacy. Completely honest, I'm not entirely 100% sure exactly how all that works. Do you guys want candy for Valentine's Day? Oh yeah, you guys do. All right, getting close to the end of the quarter. Again, if there is anything at all that you want us to cover, please let us know. So now I'm going to hand it over to Eric. He's going to talk a little bit about RNNs.
Hey folks. Happy Valentine's Day. Hopefully, we're all trying to learn some AI right now. Hopefully this workshop is going to be like the Alicia Keys to your Usher at the Super Bowl. That's the goal, all right? If not, hopefully it's not going to be like Alicia Keys' husband. Super Bowl joke. Okay. But let's talk RNNs. So previously we've worked with CNNs, and the slides are sort of like all over the place, but I'm just gonna basically tell you the TLDR. So previously, we've worked with CNNs, and what CNNs are, they're convolutional neural networks, and pretty much these are models that are tailored to recognize patterns, similarly to how like us people can recognize patterns. I'm not reading off the slides anyway. The slides are just for like, if you don't want to listen to me. But essentially, because neural networks, or CNNs, are really good at identifying patterns, they're primarily used in image recognition and processing. However, one good thing and also one limitation about a CNN is this idea that they are quote unquote feed forward. And what feed forward means is, formally, it means that your inputs and your outputs in the model are independent to each other. But when I like first heard that, I was like, I don't know what that means. So essentially, what that means is there's no sense of memory within the model. So for instance, with a CNN, they're really good at processing images, like identifying things within images. Great. However, let's say I want to process a video using a CNN. Let's say like it's a video of like a bear walking, right? To us people, we can watch this video of a bear walking and we can say, oh, this video shows a bear and the bear is walking. We see like maybe the bear like puts one paw in front of the other over time. And we're like, okay, this bear that we're watching on this video is like exhibiting walking. However, to a CNN, this is not, it'll have a really hard time identifying that a bear is walking if we input a video. And that's because the inputs and the outputs are independent. So in terms of like, if I input a video into a CNN, that'll mean that like each second of the video is sort of interpreted as something completely separate from the next second of the video and the previous second of the video. You know what I mean? So if I have a video of a bear walking and I'm a CNN processing things independently from each other, I'll look at 1 second, I'll be like, okay, that's a bear. I'll look at the second, I'll be like, we're still on a bear, but I won't be able to identify this motion of walking within the video. Does that make sense? So that's sort of the limitation of a CNN, the fact that it's feed forward. The majority of models are feed forward. So what do we do if we want to work with pieces of data that I guess like rely on like previous aspects of the data? So like if I'm on second 10 of this video of a bear walking, how can I build a model that can, I guess like, based on the fact that we were walking on second 9, we can hold that knowledge into second 10 and say, okay, we're still walking in this video. Are we still tracking? If we're not, like, please like raise your hand or like throw something at me. It's fine. So yeah, so this is like an example of like a video right here. So you can think of a video like this is what the model sees in the video, right? It's just a bunch of frames, a bunch of timestamps, right? And a CNN is sort of very overwhelmed. And let's see here. Blah, blah, blah. Oh yeah. So this is where I'm going to begin talking about sequential data. So CNNs are really bad at processing sequential data. And examples of these are things like I said earlier, like a video, where like second 10 relies on what's happening on second 9. But a lot of different things can also be sequential data. Sequential data, just to formally denote it, is like any data that has a specific ordering or relations within the data. So things such as speech recognition, that is an example of sequential data. If I record a 10-second video of myself talking and I take like half a second of that 10 seconds, I will not be able to figure out what I'm saying, the entire sentence that I'm saying, right? Another example of sequential data can be text, words, right? If I say, for instance, I like wrote down an example. If I say, for instance, the film was bad, not good, that's something completely different than saying the film is good, not bad. Exactly the same words, but the meaning is entirely different, right? This is an example of sequential data. The order of our data matters. Does that make sense so far? Tracking along? Okay. So here's the concepts. Oh yeah, RNNs represent recurrent neural networks. Essentially, RNNs are designed to be models that can process sequential data. So these are completely different from this idea of feed forward in CNNs that we were talking earlier. So like I said earlier, CNNs are feed forward. They can only process like a finite amount of things, like one thing, right? But if we have sequential data, like words, videos, sounds, this is when we want to use an RNN. And there's different types of RNNs. As you can see here, we have speech recognition, language translation, video classification, all that fun jazz. And for instance, like an example of what a CNN could see is if we have an airplane right here, is this airplane taking off or is it landing? We don't know. The CNN does not know either. So this is why we need things like RNNs to, I guess, like identify it for us, you know? So before, the general structure of a CNN of these feed-forward models is we have our input, and then we have the hidden layer. The hidden layer is essentially like the logic of our model. That's where all the magic happens. And we don't really know what happens. That's sort of the magic of machine learning and AI. And then once the model does its processing in the hidden layer, it'll output something, and that's our output, right? The difference with an RNN is now, alongside our regular input, we're going to be inputting the output of what the model outputted previously. So for instance, if I have an RNN and I input a video, and I'm currently processing second 10 of my video, part of my input for when I process second 10 is going to be second 9, maybe second 8, 7, 6, and all that. So all the differences with an RNN versus a CNN is an RNN, alongside its regular output, will also, or alongside its regular input, will also process like what's previously been outputted by the model. That's all this is saying. So if you want like a visual of like what it looks like, normally what a CNN would look like is you have like a couple nodes, and then you have, let me just write it all out here. So we have our input for our model right here, and then we have our hidden layer. Normally, sometimes there's like one layer, sometimes there's like a lot of layers, and then we'll have our output right here. And normally these are like interconnected and stuff. This would be an example of a CNN. The only difference in terms of an RNN is, for instance, with this idea of like processing a video, if I'm on like second 10 of my video, alongside my input already, I'll maybe process what the model outputted at second 9, and I'll just plug that in there, right? This is sort of all that's, I guess, new. That makes sense though? And because of this, because the model is not feed forward or forward feed or whatever, what you'll see if you actually draw, I guess, like the logic of the nodes is there's going to be a bunch of loops inside of our model because our model is basing its logic based on what is previously outputted. So inside of our hidden layer, normally in a feed forward, forward feed, whatever, it only like moves in this direction. All the arrows move this way. But in RNN, there's going to be like loops right here, and like maybe like right there, and like over there, because we are processing previous outputs from our model. This is just all conceptual. You can sort of ignore all this if you just want to get to the good stuff, but there's a lot of theory in machine learning and stuff, and that's sort of the theory. Does that make sense so far though? Cool. All right. So yeah, I wanted to explain that because like I got to like these images and like it's sort of kind of hard to read. All this is saying is the green is our inputs, the blue is our hidden layer, and the red is our outputs. So all we're saying right here, oh, you can't see my mouse. Okay. All we're saying right here is in an RNN, we have this additional input called previous hidden, call it whatever you want. But this is essentially previous output from our model. So if we're processing second 10, this would be like second 9 of our video. That's all this is saying. The diagram's sort of overwhelming, but you don't really need to care. But we hanging in there. And again, with this notion that a model in RNN will have these sort of loops inside of the hidden layer, if you were to just like completely flatten out all the loops, this is sort of like an analogy of like what that would look like. There's a bunch of like, there's not a single number on this diagram, and it's kind of a headache to read, but all this is saying is that loops can occur within the logic. And what a loop would represent is this is like logic within the model based on previous like outputs of the model. This is sort of like your model has memory, big picture. You don't really need to fully understand what I'm saying though, but this is just all theory. But we're doing all right so far. Cool. Yeah, so blah blah blah, more theory. But essentially, what is this saying here? Yeah, this is more theory stuff, so I'll just read it off. So recurrent neural networks don't use normal back propagation, but instead use a variant, or, okay, that's a typo. They use a variant back propagation through time. So we have to store, so because of this, because we have to process like previous outputs of our model, we have to be conscious of time within our model now that we build. And so because of this, we're going to have to store multiple versions of our neural network. And that's sort of, we'll talk about it in a second, but it gets sort of like a little, I guess like memory and space becomes a little bit of an issue, but not really. We're in 2024, who cares? But essentially because we have to process previous outputs of our model, we have to store multiple versions of our model. That's all this is saying here. And then we have to treat each version that we store, each like, I guess, previous output that's stored as a different layer within like our hidden layer here. So this diagram here where there's one hidden layer, that's not always true. There can be lots of hidden layers that establish the logic of your RNN. And yeah, enrolling, we mean enrolling through time, whatever. Okay, pros and cons. Let's talk about pros and cons real quick. The advantages of RNNs, ignoring all of this, you get to process sequential data. Sequential data is how a lot of data is stored these days. If you want to process a video, if you want to process sound, if you want to create like, you know, like when you're typing on Google Docs and like you're typing something and it like sort of like finishes your sentence for you, that's an example of an MLM, a natural language processing model, or NLP. I'm mixing them all up. But that's an example of an RNN. And so that's the great thing about RNNs. That's what this possibility of processing input of any length is saying. Let's see here, model size not increasing with this size. Yeah, that's pretty much the bulk of it. Essentially this idea that we can process sequential data. Two, because we can process sequential data, our model has memory. It can remember things it's previously outputted. And then three, if you want to talk math, the weights of each of our nodes are going to be shared across time. Those are good things about RNNs. Let's talk about bad things. Because we have to store multiple, I guess, like versions of our model, computation is going to be really slow. Not because like, or it's because of multiple factors. One, you just have like a lot more stuff that you're storing and a lot of more data to retrieve. And two, you have all these loops and stuff inside of your actual logic now. So that gets a little confusing for the computer too. And sort of that's the majority of the other problems listed on here are related. So for instance, difficulty of accessing information from a long time ago. Yeah, loops, history, confusing for us, just so happens to be confusing for the computer also. We can't consider any future input for the current state. Yeah, kind of sucks. Math term, more theory, vanishing gradient problem becomes very apparent over large time deltas. If you have no idea what that means, don't worry. But are we still hanging in there? Cool. All right, but that's pretty much the bulk of, I guess, the ideas of RNNs. I'm going to hand it off to the skeleton demo, which the link for that is right here.
Yeah, so before we dive right into the demo, as always, you guys know where to find all the skeletons. It's on the asset cluster. Two things. Does anyone want more candy? Yeah. Anyone else? And oh, that was That was my bad. You want to check that back here. So if you feel that you are about to get started on the RNN notebook, I would recommend taking a look up here. But if you're still working through the MNIST or like Cypher 10 notebooks, absolutely no worries. You can still do that. Us officers will still be coming around. And now I would like to hand it over to the incredible Spartan Liu.
Pull up the RNN notebook.
What? Absolutely. That is strong.
Here's the yeah. Huh? Oh yeah, no, I am. I'm just pulling up the RNN notebook first. Good. Okay.
Why would they do the question? Oh well.
Okay.
Okay.
Oh. This is the filled in version. So you guys should have access to the skeleton, I believe. Oh.
Yep.
Oh. Okay. Oh yeah, no, that's fine. We'll like split into our groups after this. I'll just run you through the demo of this real quick, and then we'll like split off. Yeah.
Wait,
Then-
you guys can't see it on the asset cluster? You guys can't see it?
Yeah, I think.
Oh, you guys don't have access to it. Okay, wait, give me a sec. Oh, shit.
Wait, why is not working?
Wait, can I see what it's saying?
I don't know.
That's crazy. I know.
So are you? No, but
Oh, you put the share link.
Wait, can you guys check the filled one now? Does it work? The filled one? Okay, good. And now the skeleton should work too. It should work.
Oh, we just updated the link. We just updated the link.
Yeah, I think it's pretty good.
Okay, is it working now? Okay,
Right.
let's zoom again. Okay, so what I'll be giving you guys today is going to be a sort of high-level overview. You'll go through this notebook in more depth when you actually get to the RNN portion, but we're just going to go through this at a very high level very quickly for now. Okay, so we've already talked about, right, how RNNs enable you to put in data in a time series order as opposed to just adding in all your data at once. So this will be the actual implementation of that. So what we're doing here is we're importing all the libraries we're going to need, which we do at the start of every program. Next, we have our tokenizer that will take our input data and it's going to sort of chunk it up into words. And each of those words is then going to be turned into a string of numbers called a vector or an embedding. So what we're going to do here is, we're going to go through our text, then we're going to tokenize all of it, and then we're going to build our vocabulary from that. Once we have our vocabulary, then we're going to set up the pipeline that we're going to use to turn our tokens into vectors. So That's what this initial part is doing right over here. Then if we go further down, we're switching our device to CUDA because we want this to run on the GPU, not the CPU. Then from here, we're passing in all of our text into our text pipeline. So what we're doing is we're going through the labels and appending that to the list of labels. Then we're going through our text, we're going through the process version of it, and then we're essentially building up our data set in this way. So that's what this entire collate batch function is doing. It's just it's going to be going through all of our batches that we have through our iterator. And then we're going to sort of transform that batch into a list of, into an input-output pair where the inputs are going to be some sort of array of words and the output's going to be the label. So now we're creating the actual model here. And again, as always, for the model, you have the constructor and you have the forward function. In this case, we also have an init weights function that's going to set all of our weights to some sort of predetermined initial value. And if we look through the model, you can see what we're doing is we have an embedding layer that's essentially going to take our input vocabulary for some given sample, run it through an embedding, through an embedding scheme that's going to return some list of numbers. Once we have that, we're just passing it in through the LSTM that we just import straight from PyTorch, and from there we just like attach a linear layer at the end of it. So the actual structure of the LSTM is not something you have to worry about as much when you're defining the model, just because, you know, PyTorch already takes care of that for you. All you have to worry about is making sure the LSTM gets in something that it's expecting, and that you take the output of the LSTM and work with it to make sure it is in the format that you want it to be. So that's why we have our initial embedding layer to turn our words into vectors. And then we have this final linear layer to turn the output of the LSTM into some kind of prediction, whether it be the token prediction or some sort of classification or whatever. Okay, perfect. So just speeding through the rest of this, you can see that we have an embedding dimension of 64, a hidden dimension of 128. And what we're doing here is we're just instantiating our model with whatever parameters that we have just to start out with. Yeah. So far, any questions about like the part where we constructed the data or where we made the model? Okay. Now going through the training epochs, this is sort of a training loop in the same way that we've been going through for the fully connected layers for CNNs and now for RNNs as well. Same exact thing, right? You iterate through you iterate through the data loader, and that will generate batches for you. And what you do is you just plug your data into your model, get the predictions, then you calculate your loss, figure out what you need to how all of the weights and biases need to be adjusted, and then actually implement the optimizer that's going to do the stepping. And then once we do there, in this case, we're also going to be keeping track of the accuracy of our model through each iteration of the training loop. So that's why we have this line here as well. And this line here is for, it's part of the optimization step, where what we're doing is we're like clipping the norm of the gradients as well. Okay, so that is our training loop. This is our evaluation loop. Again, same style as we've been doing for the past few weeks now. We set our model in eval mode, then we just iterate through the data loader, and then we get our predictions, figure out what our model's actual prediction is, compare it against what we know the actual value has to be, and then we just append both of them to some sort of counter. And then here, our evaluation is going to ultimately return some kind of accuracy, where it's going to return the total number of accurate predictions divided by the total number of inputs that are passed in during the testing phase. So now we've defined our data loaders for our training data, our testing data, and our validation. That would be these lines right over here. And then we actually implement our training loop, and that's really it. So it's sort of like in the same style as the other notebooks that we've been talking about, right? In the sense that you have the training loop, you have the evaluation loop, you're creating something to keep track of your data. That's the collate batch function, and you're defining your model here. The only difference is that your LSTM model just has an nn.lstm layer in it. That's really the core part of the LSTM as far as the actual code in PyTorch goes. Okay. So that was a really quick speed run. If you actually go to the RNN notebook, once you get there, you'll get a much deeper look into like what every single line is doing. But for now, this should be enough that you can sort of follow what the notebook is doing. So are there any questions? Okay, in that case, now we can split up into our normal groups. So in this case, I believe MNIST can go there. The CFAR10 notebook, people on the CFAR10 notebook can stay here. People who are working on the RNN notebook can go there. And yeah, we can like split up now if you guys want.